Now let's do the two main operations. We will trace Enqueue and Dequeue on the circular array, one step at a time, and watch the indices wrap. Let's enqueue a value. 3 steps, right at rear, advance rear, then add 1 to count. We start with front at index 2, rear at index 4, and count 2. Rear is the next free slot. We will enqueue 50. Step 1. We write 50 into the rear slot, index 4. The value is stored, but rear has not moved yet. Step 2. We advance rear. Rear becomes 4 plus 1, mod 5, which is 0. Watch it wrap past the end, from index 4 back to index 0. Step 3. Count goes from 2 to 3. One more element now lives in the queue. Now the same work in C. First, the code checks if the queue is full. If it is full, it returns 0 and stops because there is no room. Next, it writes the value. It sets queue arrow data at index queue arrow rear to V, that is the free slot rear points at. Then it advances rear. It sets queue arrow rear to queue arrow rear plus 1, mod queue arrow capacity. The mod makes rear wrap back to 0 at the end. Finally, it adds 1 to count. One more element now lives in the queue. The cost is big O of 1. 1 write, 1 modular add, 1 increment. There is no shifting of elements ever. Now let's dequeue. 3 steps. Read the value at front, advance front, then lower count. We continue from front at index 2, rear at index 0, and count 3. Step 1. We read the value at front, which is index 2. That value is 30, and we return it to the caller. Notice we do not erase the cell. Step 2. Advance front. Front becomes 2 plus 1, mod 5, which is 3, and count drops from 3 to 2. Index 2 still shows 30, but it is now unused outside the queue. Now the C first it checks if the queue is empty. If it is empty, it returns 0 because there is nothing to remove. Then it reads the value at index front and copies it out to the caller through the out pointer. Next it advances front. It sets queue arrow front to queue arrow front plus 1, mod queue arrow capacity. Front wraps around the same way rear does. Then it subtracts 1 from count. 1 fewer element now lives in the queue. The cost is big O of 1, the same shape as in queue. 1 read, 1 modular add, 1 decrement. Now a common mistake. Suppose a student writes queue arrow front equals queue arrow front plus 1 and forgets the mod queue arrow capacity. What goes wrong the first time front reaches capacity minus 1 and dequeues again? Think about it. Now the answer. Front becomes equal to capacity, 1 index past the last valid slot. The next read is out of bounds. In C, that is undefined behavior, not a clean error you can catch. Your turn again. The ring is full, capacity 5, with front and rear both at index 2 and count 5. Since it is full, front equals rear and count tells us which. Dequeue once. Which value comes back, where does front move, and what happens to the old cell? Predict first. First part. Dequeue reads the value at front, index 2, which is 30. That is returned to the caller. Second part. Front becomes 2 plus 1, mod 5, which is 3, and count drops from 5 to 4. Third part. C2 still holds 30 in memory, but it is now unused. It is outside the queue, and a later enqueue can overwrite it. Your turn. This ring is empty, capacity 5. Enqueue A, then B, then C, then dequeue once. Then enqueue D, predict the final front, rear, and live seats before each row appears. In queue A, we write A at rear, index 0, then rear moves to 1. Count is 1, and seat 0 holds A. In queue B, rear moves to 2. Count is 2, A at 0, B at 1. In queue C, rear moves to 3. Count is 3. Seat 0, 1, 2 hold A, B, C. Now deque. We read A at front, index 0, then front moves to 1. Count is 2. Seat 0 is free again right away. On the ring it is reusable. In queue D, we write D at rear, index 3, then rear moves to 4. Final state. Front is 1, rear is 4, count is 3. Live seats are 1, 2, 3, holding B, C, D. One more check, this time with the wrap. Capacity 5 start empty. In queue 10, 20, 30, 40, deque twice. Then in queue 50 and 60, where do front and rear end up? Predict first. Now the answer. After 4 enqueues, front is 0 and rear is 4. 2 deques move front to 2. In queue 50, rear becomes 4 plus 1 mod 5, which is 0. It wraps. In queue 60, rear becomes 1. So front is 2, rear is 1, count is 4. Rear has wrapped past the end while front has not caught up. To enqueue, we link the new node after the current rear, then move rear to it. That is 2 pointer rights and nothing has to move. Watch the new node in green. Step 1. We call malloc and get a fresh node at 3000. It holds the value 30. Its next field is already null, so the node is not linked to the queue yet. Right now front names node 10 and rear names node 20. Step 2. We set rear arrow next becomes X, so node 20's next field now holds 3000, the address of the new node. Rear itself has not moved yet. Step 3. We set rear becomes X, now rear holds 3000, so it names node 30. The enqueue is done. It is big O of 1 because there was no walk to the tail. The order matters and swapping it is not harmless. Link the new node first, with old rear arrow next becomes X, then move rear with rear becomes X. If you move rear first, then the next line rear arrow next becomes X actually sets X arrow next to X, the node points at itself. And the old rear still has next equal to null, so it is cut off from the new node. The queue is broken. So always link first, then move the pointer. Now the same in Enqueue and C, the function is called Enqueue. It takes the queue pointer Q and a value V, and it returns 1 on success or 0 on failure. First we call malloc to ask for 1 queue node of memory. We keep the address in a new pointer called X. Next we check the result. If X is equal to null, malloc failed. We return 0 and leave the queue unchanged. Now we fill the node. We set X arrow data becomes V, so the new node stores the value. We set X arrow next becomes null. The new node is always the last one in the queue, so nothing comes after it. Now we ask, was the queue empty? We check if queue arrow rear is equal to null. If it was empty, we set queue arrow front becomes X. The new node is now both the front and the rear. Otherwise the queue already had nodes, so we set queue arrow rear arrow next becomes X. This links the old rear to the new node. Either way, we set queue arrow rear becomes X. The new node is now the rear. Last we return 1 to say the enqueue worked. To deque, we save the old front, advance front, then free the old node. If this empties the queue, rear must also reset to null. The order matters, so watch it 1 step at a time. Step 1. We set old becomes front 1000. Then we read old arrow data, the value 10, so we can return it later. Front and old both name node 10 right now. Rear names node 30. Step 2. We set front becomes old arrow next 2000. Front now names node 20. Node 10 is unlinked from the queue, shown grayed out, but old still holds it, so it is not freed yet. Step 3. Now we call free of old, so node 10's memory is released and it disappears. We return the value 10 that we saved earlier. The dequeue is done and it is big, O of 1. Now the dequeue in C, the function is called LQDQ. It takes the queue pointer Q and an out pointer, where it writes the value it removed. First the guard. If Q arrow front is equal to null, the queue is empty. There is nothing to remove, so we return 0. We save the front node in a pointer called old, before we change anything. We set the value at out becomes old arrow data. This copies the front value out to the caller. Now we advance. We set Q arrow front becomes old arrow next, so front moves to the next node. Then we ask, is the queue now empty? We check if Q arrow front is equal to null. If it is, we set Q arrow rear becomes null. Rear must follow front down to null, so it never points at a freed node. Now it is safe to call free of old. We only free after we have saved the value and moved the pointers. Last, we return 1 to say the dequeue worked. The whole dequeue is big O of 1. 1 read, 1 pointer move, and 1 free. Let's do a quick check. Suppose you dequeue the last node. The code sets front to null, but a student forgets to also set rear to null. What breaks on the next enqueue? The answer. Enqueue checks if rear is equal to null to see whether the queue was empty. If rear still points at the freed node, enqueue instead does rear arrow next becomes X on that dead node. That is a use after free bug. Now the edge case, dequeuing the last node. Here front and rear both point at the same node, node 40, at 1000. Watch what has to happen to rear. Step 1. We set old becomes front and read old arrow data, the value 40 to return. Both front and rear still name node 40. Step 2. We set front becomes old arrow next, which is null. Now the check fires. If front is null, set rear to null too. So both front and rear are null. Node 40 is unlinked, grayed out, but old still holds it, so it is not freed yet. Step 3. We call free of old and node 40 is released. The queue is now empty, with front and rear both null. The key point. When old arrow next is null, the queue just emptied, so rear equals null must run before free of old. Miss that line and rear dangles at a freed node, exactly the bug from the last check. Let's run the circular queue, capacity 5, and read the output 1 call at a time. Watch rear wrap around, the queue fill up, and a full queue in queue get rejected. We enqueue 10, 20, 30, 40, then print all 4 values in order. Front is 0, rear is 4, count is 4. Rear points 1 past the last value. The first dequeue returns 10, the oldest value, the first one that went in. The second dequeue returns 20. Now the print shows 30 and 40. Front has moved to 2, rear is still 4, count is 2. Now enqueue 50. Rear was 4, so it becomes 4 plus 1 mod 5, which is 0. Watch it wrap from 4 back to 0. The contents are 30, 40, 50. Enqueue 60. Rear moves to 1, count is 4 now. Enqueue 70. Rear moves to 2 and count reaches 5. The queue is full, and notice front and rear are both 2. Front equals rear and count tells us it is full. Now enqueue 80. The queue is full, so the full guard rejects it and prints a rejected message. No live cell is overwritten. The output is deterministic, values and indices only, no raw addresses, which follows the rule from Chapter 1. A deck needs 4 operations instead of 2 because you can add and remove at both ends. All 4 keep the same convention. Front is the next slot to read, rear is the next slot to write, and count is how many are live. Push front. We move front back first. Front becomes front minus 1 plus capacity, mod capacity, then store the value there. It is big O of 1. Push back. We write it rear first, then advance rear. Rear becomes rear plus 1 mod capacity, also big O of 1. Pop front. We read the value at front, then advance front, front plus 1 mod capacity. Pop back. We move rear back first. Rear minus 1 plus capacity, mod capacity, then read the value there. Let's watch 2 of them on an array capacity 5. We start with front at 0, rear at 2, count 2. 10 and 20 are live. Push front of 5. Front becomes 0 minus 1 plus 5 mod 5, which is 4. It wraps to the last seat. We write 5 there and count is 3. Notice the cells stay in place, 0 through 4, only front and the value moved. Push back of 60. We write 60 at rear, index 2, then rear advances to 3. Count is 4. Front is still at index 4. The one new idea is that push front moves front backward, wrapping past index 0 to the last index. That is the opposite of push back. Each guard checks count. Reject a push when count equals capacity. Reject a pop when count is 0. And we add capacity before the mod so C never sees a negative number. Your turn. We have an array deck with capacity 5 and front is at index 0. We call push front of 99. There is no seat to the left of index 0. So where does the new front go? Predict before you look. Now the answer. Front becomes 0 minus 1 plus 5, mod 5, which is 4. It wraps around to the last seat. Adding capacity first is what keeps C's mod from ever seeing a negative number. FIFO order is not just bookkeeping. It also decides what gets found first. This is a small preview of breadth-first search. The full search is Chapter 15. Here we only watch the queues roll, starting from node 0. We start by marking the start node as visited, so we never process it twice. Then we seed the queue. We enqueue the start node, so the queue has 1 node to begin with. Each pass, we dequeue the front node into U, using the same outparameter form as CQDQ. Because it is FIFO, U is always the oldest node we have discovered. Then we scan use neighbors. For each neighbor V, we check whether V has been visited yet. If it has, we skip it. If V is new, we mark it visited right away, at discovery, so it never enters the queue twice. Then we enqueue. The newly found nodes join the back of the line, so they are handled after everything already waiting. Look at the graph. Starting from 0, the queue spreads the search out layer by layer. Level 0 is just node 0. Level 1 is 1 and 2. Level 2 is 3, 4, 5. So the visit order is 0, 1, 2, 3, 4, 5. Now swap the queue for a stack, and the very same loop becomes depth-first search. The container's rule decides the search order, not the shape of the loop.